Jeez. All right, so I can balance this out by putting a 2 in front of those waters to balance out my oxygens. Then I need to update this to a 2 to balance out those hydrogens. When we're building our equilibrium expression, we're going to remember what? What over what? Products over reactants. And this one, I'm specifically asking you for Kp. What is that P for? Pressure, right? So I'm going to make my equilibrium constant in terms of the pressure of these gases. So products, the pressure of H2, pressure of O2, and then what happens to these coefficients? They become exponents in my equilibrium expression. So that means I need to do not just H, the pressure of hydrogen gas, but the pressure of hydrogen gas squared, right? My coefficients become exponents. Divide that by the pressure of the water vapor squared. Okay, so now how can we use this information, right? So we're going to be doing some, again, everybody have a calculator here. We're going to be doing problems that require a little bit more algebra than what we've done up until now. Okay, and so what type of problem would this look like? All right, so we have an initial pressure of water vapor is 2.15 atm, right? So I'm going to stick some steam into a closed vessel here, and initial pressure is 2.15 atm. Then I'm going to allow this reaction to occur and to reach equilibrium. And now the pressure of the water vapor, first of all, what do we think? Is it going to go up or go down? If I have this initial amount of water and then all of a sudden some of this reaction occurs where it gets converted into hydrogen gas and oxygen gas, does the amount of water go up or down? Down, right? It's reacting and forming those two products. So now at equilibrium, the pressure of my water vapor is 0.75 atm. What is the value of Kp? Okay, so using this information here, we're actually going to be able to determine the value of Kp in this reaction. All right, so how are we going to do that? We're going to build what's called an ice table. And we're going to use this ice table in a variety of different settings throughout the course. So this is our first sort of introduction to an ice table. I stands for the initial concentration or pressure. That's not how you spell initial. Maybe it is. The C in our ice table is the change that occurs. And then the E on our table is the value at equilibrium. Okay, so those are our rows, and then for our columns, we're going to have all of our components of this reaction here. So the water vapor and our two products, the hydrogen gas and the oxygen gas. Right, so for each one of these species, we're going to input its initial value, the change that occurs when the reaction happens, and the equilibrium value. Okay, so what is the initial pressure of the water vapor in this problem? The 2.15 atm. And how much hydrogen gas and oxygen gas do I have initially? 0, right? Before any reaction has occurred, I don't have any of that stuff. Okay, and then the whole thing about how this works is this change row is going to be very important. Let's get our balanced chemical equation down here so we can look at it. Okay. So, how much of each of these is going to change, we don't know. So we're going to use this variable, okay? We're going to say that our reactant, because it's being consumed, is going to decrease by some variable x, and our products are going to increase by that variable x. Okay? The one thing that I need to make sure to include is these stoichiometric coefficients. Right? So for every quantity that decreases, it's going to be 2x for my reactant because of the 2 in my balanced chemical equation. And it's going to be increased by 2x for hydrogen gas because there's a 2 in that balanced chemical equation. Right? So our stoichiometric coefficients are going to appear in this change box along with this variable x. Notice that for oxygen, because there's just a 1 here, that's just going to increase by x. Right? And so if you think, like, if we look at just these two boxes right here to try to make sense of it, this is saying that for every 2 water molecules that react, I'll get 1 molecule of oxygen gas. And that's the same thing that we're saying in our balanced chemical equation up here, right? If 2 water molecules react, I'll get 1 molecule of oxygen gas. Okay, so let's just make a note. Let me make some room. All right, so if we can make some notes on terms of how we're filling this out, our change box, reactants decrease, and products increase. And we're going to include, those stoichiometric coefficients with the variable x. All right, and then our equilibrium box is the initial plus the change. right, so for each one of these, in order to get that last row, I'm just going to sum up the first two rows. So in this case, it would be 2.15 minus 2x. This would be 0 plus 2x, or just 2x. And this would be 0 plus x, or just x. Excuse me. Okay. Now, why did we build this ice table here? Because now we know what the equilibrium value is for each one of the components in our expression for Kp. So I can go back and fill in this expression for Kp, replacing each one of these pressures with their corresponding equilibrium box. So Kp equals the pressure of hydrogen gas. So look, so this variable here, I'm going to replace with 2x. So that means it becomes 2x squared. I'm going to replace this one here with x. And then my bottom one is 2.15 minus 2x. I'm going to make sure to square that. All right, so for each one of these, I took my equilibrium expression, pH squared PO2 over pH2O squared, and I replaced each one of these pressures with their equilibrium values from the ice table, right? Because it's an equilibrium expression. Okay, so my pressure of H, replace that with the 2x. That's how I got the 2x squared. My pressure of O2 was x. That's why I have this x in the equation. And then my pressure of my H2O was this 2.15 minus 2x. And so that's how I got this 2.15 minus 2x squared in my equilibrium expression. So if I can figure out what x is, I can plug it in here, and then I'll have the value of my equilibrium constant, and that's what we're going for here. Okay? So in this case, how am I going to get the value of x?
The final water vapor.
Exactly, right? So here it tells me that the final pressure of water vapor at equilibrium is 0.75, right? That means that my 2.15 minus 2x, I already know what that equals. The equilibrium value is 0.75. So I can set this P of H2O at equilibrium is what was given, that 0.75 atm, which is that 2.15 minus 2x. All right, because that was my equilibrium for water. All right, so everybody take a second and solve this for x for me. Let's practice our algebra here. Whoop. All right, so if we rearrange and solve for x, we're going to subtract 2.15 from each side. That would get me negative 1, what is it? Negative 1.4 equals negative 2x. Divide both sides by negative 2. Right, so if I do my algebra and solve, I find that x is equal to 0.7. And then what am I going to do next? Turn around and plug it back in, right? So now that I have my x value, I can turn around and plug it back in into this formula here to solve for Kp. All right, so 2 times 0.7, square that, times 0.7, divided by 2.15 minus 2 times 0.7 squared. Did you have a question? We do, you're right. Yeah, but just kind of to keep it simply just plugging back into that formula there. You're right, we know what the 2.15 minus 2x is. So you could absolutely plug that value in there as well. Get the same answer either way. All right, so we plug that back in, punch all that into our calculator, and we get the value of 2.44 for our Kp. All right, so again, using our balanced chemical equation, starting with the initial value of each of these quantities from our problem, we can then create this change box using the variable x to indicate how much that pressure is going to change by. Reactants go down, so they get a negative sign. Products go up, so they get a positive sign. And then we just have to make sure to include those stoichiometric coefficients in that change box as well, since that locks in the ratio by which these two change by. Okay? So what if instead of asking for Kp, I had asked you for something like what is the pressure of O2 at equilibrium? How could you use what we've done to solve for the pressure of O2 at equilibrium? Well, according to our ice table, what's the pressure of O2 at equilibrium? X, right? At equilibrium, my O2 pressure is X. So then what would be the pressure of O2 at equilibrium now that we've solved for X? Pressure of O2 is just that 0.7 atm. So then what about the pressure of hydrogen gas? What would that be? How'd you get that? 2x, right? Because according to my ice table, at equilibrium, the pressure of hydrogen gas is 2x. All right, so 2 times 1.7 gives me 1.4 atm. Okay? That's what our ice table is doing for us. Granted, it's in terms of these variables, but it gives us our quantity for each of those at equilibrium, right? Or rather, the value of each of those pressures at equilibrium. Because pressure of hydrogen gas, hydrogen at equilibrium is 2x, and we established that x was 0.7. So 2 times 0.7 is 1.4. All right, so let's do another one here. All right, we're going to do this one in terms of Kc. So give me my Kc expression. Yep. Okay, so I'm going to build my expression Kc. C, so C is concentration. Again, products over reactants. So concentration of that CH2O squared divided by the concentration of C2H4 and O2. Okay, so now for this problem, I'm not asking you for Kc. I'm going to give you Kc, all right, as well as the initial concentration of these reactants. And we're going to be able to use this same strategy we did last time to figure out what the concentration of all these gases are at equilibrium. Again, we're going to build our ice table. All right, I want you guys to try to fill in this ice table as best you can on your own. All right, what's the initial value for that C2H4? One more time, what's the initial concentration of C2H4 for my problem? 3.42. All right, that's the initial concentration. This is the value of that equilibrium constant, but the initial concentration is 3.42. And what's the initial value of the O2?
Isn't it adding, so wouldn't it be
Isn't adding.
like C2H4 plus O2 is...
Oh, I meant both of them. I see what you're saying, but no, I meant, got it. All right, this is how I do and. I know that that is a big pain in the ass, but this is a plus sign. This is and, all right? So my bad, y'all. No, this meant that the concentration of C4H2 and O2 is 3.42. I see the confusion. My bad, my bad. Both of them are 3.42. Okay, my bad. All right, so what I was trying to say is that the initial concentration of both C2H4 and O2 is that 3.42 molar. So then what's the initial concentration of my product? 0. All right, so now we need to do our change box, right? So reactants, do they increase or decrease? Decrease. So this is going to be minus X. And there's no stoichiometric coefficient out front, so it's just X. All right? What about my next box? What goes here? Minus X again. And what about this box? What goes here? Plus 2X, right? So it's a product, so it's going to be plus. And it's got that stoichiometric coefficient of 2, so it's going to be plus 2X. Right? And it's saying the same thing as our balanced chemical equation. For every one oxygen molecule that reacts, I get 2 of these products. Right? That's what my balanced chemical equation is saying. That's what our change box is saying as well. All right? So now I can figure out my equilibrium box by, again, summing up those first 2 rows. So this is 3.42 minus X. 3.42 minus X, and 0 plus 2X is just 2X. All right, now we've already built our equilibrium expression. Now you just need to fill it in with the information from our ICE table. All right, so see if you can't do that. Substituting these variables here. This was our goal in life, was to replace these with variables from our ICE table. All right, what am I going to put in place of the concentration of CH2O? 2X, right? Don't forget that exponent. That's the biggest mistake that people make. This isn't just 2X, but 2X squared, right? Because this here in orange, I'm going to replace with my 2X, but it's squared in that expression, right? So I need to make sure to keep it squared when I fill in my variables. What am I going to replace this with? 3.42 minus x. And then what about this one here? Same thing, right? Comes from this box here. Okay, so before we move on, I want to make extra special sure that everybody can see how I was able to use that ice table and my equilibrium expression to then fill in those variables on my equilibrium expression, right? Now everything in that equilibrium expression is in terms of just one variable, x, instead of all these unknowns here, all these unknown concentrations, right? If I'm going to do a math problem, I can only have one variable missing. I can't have three different quantities I'm trying to solve for, right? So that's why we build our ice table, to put everything in terms of just that single variable x that then we can load back into that equilibrium expression. Did somebody over here have a question? You're going to always put a negative next to it. In your calculation, if it turns out that they go up, then you'll just get a negative value for x. So it'll always work out that way, okay? All right, the other thing I'm going to do just to make our lives easier is I'm going to simplify this denominator real quick, because 3.42 minus x times 3.42 minus x is just 3.42 minus x squared. Right, so I'm just going to do this. Boom. All right, and again, I can only have one variable, so in this particular problem, the other thing that I'm given is that value of Kc. Right, so I don't know what x is, but I do know that all of this business over here has to equal that 0.763. All right, and although this is going to be a bit of a pain in the butt and require some algebra, this equation right here has just one missing variable. So I can do some algebra, rearrange, and solve for x. All right. So in the interest of time, we'll do this together. There's actually sort of multiple ways you can go about it. You could sort of leave things, expand it and then do this quadratic equation. The negative b plus or minus square root. Anyways, we don't have to do that because luckily both of the top and the bottom are squared. So this can simplify to 2x over 3.14 minus x squared equals 0.763. And so how can I get rid of that square? Take the square root of both sides. Oh, my bad. I'm thinking pi. Pi on the brain here. But yes, I can now get rid of it by just taking the square root of both sides. All right, so now I've got 2x over 3.42 minus x equals that square root of 0.0763. I could figure out what that number is. I'm just going to leave it like that and punch it into my calculator like that. But if you wanted to, figure out what the square root of 0.763 is, you could do that. So what am I going to have to do next in order to solve for x? I got an x on top here and an x on bottom here. I'm going to eventually have to combine them. I'm going to have to move that denominator over to the other side, right? So how do I move that denominator? What do I do to both sides? Multiply by the denominator. Look, you can do anything you want to an equation as long as you do it to both sides, right? So I'm going to multiply this side by 3.42 minus x and multiply this side by 3.42 minus x. I'm going to do that because that'll cancel it out over here. So now I have 2x equals the square root of 0.763. Okay, See if you can't finish this off. All right, so like I said, there's going to be quite a bit of algebra here. Is this the easiest algebra problem in the world? No, absolutely not. But it is doable, right? We can sort of rearrange and solve. So multiply both sides by that denominator. Then I got to distribute so I can separate x out. So I distribute that 0.736 to both of those terms. Now I can move everything with x over to one side and pull out that variable x. And finally then get x by itself by dividing by that 2 plus the square root. Okay? So real quick, the question was, so if we say x is 1.04, what would be the equilibrium concentration of the C2H4? 3.42 minus x, right? So 3.42 minus my 1.04, or 2.38. Same thing over here. And then what would be the concentration of my product at equilibrium? 2 times x, right? So the 2.08 molar. All right? So, again, it's a little bit more algebra than we've seen thus far, but should be totally doable. What's up? No? Cool. There is, but not in this course. But yeah, totally, absolutely. Yep. What up? What's up?
I have a question about the exam.
Uh-huh.
So